So, so I'll just get right into it since I don't have too much time. So the conjecture that we're interested in, and unfortunately we're not going to prove yet, is let A over Q be an abelian surface and just for safety's sake, let's assume that it has no non-trivial endomorphisms. Then there exists a Siegel cusp eigenform F weight 2 and genus 2, so that just means for GSP4, such that the L function of the abelian surface is the L function of this Siegel modular form. And by this, I mean the sort of degree 4 spin L function associated with Siegel modular form. And if you're wondering, the only reason I wrote this is just for safety's sake. We want to make sure that this should really sort of correspond to a Siegel cusp form, and not maybe some kind of Eisenstein series or something like that. And so, anyways, I'm just going to go ahead and state the theorem that we proved. So the theorem, let me actually just go over to the next board. So the theorem that we proved is the following. So let A over Q be an abelian surface. And suppose following hypotheses. So first, I'm going to assume that A has a prime to 3 polarization. And moreover, and this is sort of the important thing, the 3 torsion Galler representation is surjective. So I'm going to write rho bar A3, which is the sort of the Galler representation on the 3 torsion. Since I've assumed there's a prime to 3 polarization, this can be viewed as a Galler representation valued in GSP4 F3. And I'm going to assume that this is surjective. Not totally necessary, but in some sense, it doesn't weaken the theorem significantly. So let's just state it like this. I'm going to assume that A has good ordinary reduction at 3. Again, it's not totally necessary, but it doesn't really matter. I'm going to assume that A is 3 distinguished. There are lots of 3s in this term. So this means that Frobenius at 3 has distinct eigenvalues. The distinct characteristics are like, for example, the L-adic tape module for L not equal to 3. And so you might have you can kind of anticipate why I like hypotheses like these. And then there's a kind of weird one, which we also expect to get rid of in the not too distant future. And that is the following. So I'm going to assume that this 3 torsion representation is unramified at 2. And moreover, if you look at Frobenius of 2, this does not have order 4 or 12. Okay. Now I've left myself no room to write the statement of the theorem, but I guess you can kind of guess. Then A is modular. Okay, so I don't have much time, and basically my goal for today is to give you a kind of overview of the strategy of proving this theorem. So I'm not going to give a huge spiel about what was known before, but basically, I mean, about 10 years ago, it was not known that a single abelian surface with Mumford-Tate group GSP4 was modular. Then various groups of people proved that like a couple of them are modular by basically finding the modular form and using something like the Faultin-Serre method to prove that it is really modular. Then we, with the same group of people, so BCGP, we proved potential modularity, which which gives you the meromorphic. So one reason you might care about this is to get prove the Husserl conjecture, the holomorphic continuation of this L function. That at least gives you the meromorphic continuation, but we still want this kind of honest modularity. And we also proved that like infinitely many of these general abelian surfaces are modular. But this theorem, we view it as a big improvement because it's kind of, well, it's not proving that all abelian surfaces are modular, but at least it applies a lot of the time to at least like a positive proportion. And so, for example, we can write a function in magma like is provably modular that takes in a genus 2 curve and tells you if it's Jacobian is provably modular. And you can go through the LMFDB and the like 60,000 genus 2 curves in their table, and it's more than 15% of the time the answer is yes. Whereas before, your is provably modular function might as well have just printed out no. It would have made no difference. Okay, good. So the strategy, well, to be honest, I mean, there's basically all such theorems are proved in roughly the same way, and it's a strategy which is dating back to the work of Wiles on the modularity of elliptic curves, and we're really just rehashing this over and over again for the last 30 years. So the strategy is, well, we're going to prove a modularity lifting theorem. And that's the kind of statement that says that if you can prove that the p-torsion Galois representation is modular, then that implies that A is modular. This is this sort of technique introduced by Wiles of propagating modularity through congruences. And of course, I mean, there's going to be lots of hypotheses in that statement, and we'll get into that a little bit more. And then, of course, if you have such a statement, you still need to prove that AP is modular for some P. And so that's the sort of residual modularity. So we need some kind of strategy for getting started. And so basically, like a good way to view the subject is like this part is kind of science. And indeed, that's where we're going to sweat a lot. And then this part of the subject is kind of, as going back to Wiles, some kind of shenanigans and tricks and doing something a bit clever. So I'm going to actually start by talking about this part first, because it's the kind of fun part, but I really hope I'll get also to talking about this, because that's what has to do with p-adic automorphic forms. Okay? So let's start with this. So we're going to do some kind of 2-3 switch. So Wiles did a 3-5 switch, but there are 2-3 switches in the literature, and we're going to do a 2-3 switch. So what does it mean? So given our abelian surface A that we want to cook up as modular, we're going to cook up another abelian surface that we're going to prove is modular first. And so the way that's going to work is, so given A, we're going to construct B, which is going to be the Jacobian of some genus 2 curve, C, which is of the form y squared equals f of x, where f has degree 5. So as I'll explain in a moment, this is a sort of special kind of abelian surface because this f has degree 5, and we'll discuss in exactly what way it is in a bit. With so some desired properties. So the first one, and of course the most important one, is that the 3-torsion Galois representation of this new abelian surface should be the same as the 3-torsion Galois representation of the one we're trying to prove is modular. And so this is going to allow us to basically say that B is modular implies A is modular, at least if we have a suitable modularity lifting theorem that applies in this setting. Okay? So, and then the other things are a bit less important. So we're going to, well, they are important, but we're going to ask that the Galois group of this polynomial contains A5. And then we're going to ask some kind of two-adic stuff about this new guy. So we're going to ask that B is ordinary at 2, and also 2 distinguished. And probably something else that I'm forgetting. I can move up this board in the meantime. Yeah, okay, yeah, of course. There's something at R also. So we want that F has 1 real root. Okay, so I'm not going to explain exactly how we prove that such a B exists, but actually it's surprisingly easy. And I'll just basically say in words, it's basically something that we proved in our previous work. So you look at the moduli space of genus 2 curves, which have a rational Weierstrass point, which is what it means for it to be of the form y squared equals f of x, where f has degree 5, as well as a sort of twisted full level 3 structure, which is what we're putting here. And you prove that that moduli space is a rational variety over Q. And so once you have a rational variety over Q, it has lots of Q points. And in particular, you can put whatever local conditions you want, as long as those local conditions are locally possible. And so well, this is no problem, but this sort of two-addict condition, it's exactly where something is being used about the 3 torsion representation at 2. And it's just a sad fact of life that there aren't very many genus 2 curves over F2 over Q2, and you just use what you get, okay? Of course, if you can make some base change or something, you'll easily deal with this. So we don't expect this to be a serious problem. But anyways, so anyways, that's how you find this B. And of course, now you have to prove that B is modular. So now this is the next part of the trickery. So this is the sort of residual modularity. Two, and here, this argument was actually discovered, well, really before us, by Suzuki and Yamauchi. And so the idea is like this. So we're going to look at the 2 torsion representation of this abelian surface. And so we have the rho bar B2 from GQ to GSP4 F2. Well, what is GSP4 F2? Well, it's isomorphic to S6, where this is the permutation group of the 6 permutes the 6 Weierstrass points of C. And so we've assumed that there's a rational Weierstrass point. And so it means that actually this Galois representation is factoring through sort of S5 or A5, because I also assumed that the Galois group of F was big. And so let's assume that the image is A5. In fact, we can't really arrange that, but what we actually do is just base change to the real quadratic field over which it becomes A5. And it is indeed a real quadratic field because we've ensured that complex conjugation is in A5. Okay. Now what? Well, okay, so I'm going to draw some diagram. So we have the Galois group, a bit bigger. We have the Galois group of Q. I've assumed that it acts through A5. But now A5, it also has a 2-dimensional mod 2 representation. Actually, it has 2 of them. Sorry. And it doesn't really matter which one I choose for the following purposes. And the relation between this 2-dimensional representation and this 4-dimensional representation is that this is actually the symmetric cube of this. At least it's isomorphic to it. So this representation, it can't be realized over F2, obviously. It's realized over F4. And its symmetric cube is this 4-dimensional representation. Now, what is rather juicy, of course, is that A5, well, it doesn't quite have a 2-dimensional complex representation, but it has a 2-dimensional projective complex representation. And so what that means is that by a theorem of Tate, some central extension of it gives us an Artin representation. This is a central extension, which has a 2-dimensional representation, which we can arrange to lift this mod 2 representation. So you can imagine, I mean, this representation has finite image I'm viewing it as a sort of two-adic representation, but you could also just view it as a two-dimensional complex representation. And it's odd, again, because of this. So this thing, which I'll call rho tilde, is an odd Artin representation. Okay, so now what do? Well, this gives us one modularity of such things. The weight one modular form. This was proved by Carvant and Berger. This gives us a weight one modular form. We construct the congruence mod 2 with a weight 2 modular form. And then we take its symmetric Q, which gives us a weight 3 Siegel modular form. We'll call capital F. And this gives us, in some sense, residual modularity for our abelian surface B at t equals 2. And sort of rho bar 2 is the same as the, let's call it F, or something like this. Okay, so we're happy. But now there's the question of actually proving the modularity lifting thing. And so here I'm going to emphasize, so in our past work, the modularity lifting theorem required residual modularity in weight 2. But what we've actually constructed is a higher weight modular form, which is this, and so, well, I don't really have time to properly explain this, but you should think that weight 2 Siegel modular forms are more like weight 1 elliptic modular forms, and a weight 3 Siegel modular form is like a weight 2 or higher elliptic modular form. And so in order to apply the modularity lifting theorem from our previous work, we would need to somehow produce a congruence between this weight 3 modular form and a weight 2 modular form. And the honest truth is, well, I think this is a very interesting problem, but we don't really know how to do this. So we need to do something actually totally different. And of course, for this other step at 3, we could use our old theorem, but it's really for this thing at 2 that we need to do something else. So what are we going to do? Well, basically, this whole strategy, we had it several years ago, and we didn't really have any way to proceed. But then a miracle occurred, and that miracle was a paper written by Louis Pon. And so we're going to use Louis Pon's ideas. So the strategy for the modularity lifting theorem, it's sort of like this. So the first step is we do ordinary p-adic modularity lifting. To attach to, well, A or B or whatever abelian surface we're trying to prove is modular, an ordinary p-adic modular form. And then, well, in some sense, this is kind of the easy part. I mean, this kind of modularity lifting theorem, it's the kind of thing that we knew how to do for a long time, with some slight caveat having to do with the fact that maybe P is 2 and maybe the residual image is not too big, but that's only for the connoisseurs. So you should view this as kind of pretty standard these days. And then the next step is just to prove that that p-adic modular form is classical. So prove that it is classical using the technique Louis Pon. Okay, so I'm going to try to just give basically a brief introduction to how this looks in the situation of GSP4. And I apologize, I won't really be able to go into too much detail. So, okay, so I need to talk about p-adic modular forms. Finally. And so I'm going to be working in the setting of sort of coherent cohomology, so I need to introduce the space that these forms are going to live on. And so X is going to be a Siegel threefold with Iwahori level at P. And so what that means concretely is it's the moduli of an abelian surface, say maybe a principal polarization or just a polarization of some fixed degree. And then the level at P is some flag of subgroups inside the P torsion, where this has order P, this has order P squared, and is isotropic. This is just the usual description of the Schmorr-Vardiet Iwahori level. And I'm going to draw a picture just so I can point to this picture and describe where various kinds of p-adic modular forms live. So this is a picture of maybe the sort of rigid analytic generic fiber of this space. And I mean, everything is actually sort of over QP and in the world of analytic geometry. So I like to picture this space as maybe some kind of parallelogram like this. Okay, maybe I should make the picture a bit bigger. And this parallelogram, it has some kind of corners, and those corners are the different components of the ordinary locus. There are sort of four components of the ordinary locus. And the way that you describe the four components of the ordinary locus is somehow giving the relative position of this flag with the canonical subgroup. And so we like to label them by elements of the Wall group, but I'll be more gentle and just label them as follows. I'll write XMM, so M stands for multiplicative, XM et, X et M, and X et et. And so what the notation means is you just look at whether or not this group H1 or this group H2 mod H1 is multiplicative or étal. So for example, XM, it's the locus where A has, say, good ordinary reduction. I'm not really worried about the boundary. And say H2 is equal to the canonical subgroup. So both H1 and H2 mod H1 are multiplicative groups. So now we can consider some spaces of p-adic modular forms. So traditionally, we define p-adic modular forms sort of on or in an overconvergent neighborhood of this chunk of the space. So we can consider overconvergent modular forms, which are like the H naught of some kind of Dagger or overconvergent neighborhood of this thing. And so these are overconvergent modular forms. And inside that, we can talk about the ordinary p-adic modular forms, which I'm just going to denote like this. And then that contains inside it the actual classical modular forms of weight K. These are sort of classical modular forms.
Also want to add an ordinary superscript.
Yes, thank you. Yeah. Ordinary classical modular forms. Thank you. Okay, so I'll erase this, but not my picture. So there's a classicality theorem in Hito theory, and what it says is that when K is bigger than or equal to 3, these two spaces are the same. This is somehow Hida's classicality theorem. Whether or not Hida exactly proved this, he actually did prove something close to this, maybe for k sufficiently large. Question?
For t equals 3, who is it due to?
Honestly, yeah, I don't know. So maybe when maybe we can discuss this afterwards. If this is true, I mean, maybe it is true. And there is a proof in some of our papers, but I'm not sure if, for example, for P is 2, it was proved before. Maybe let's not worry about that. Okay, so but not when k is equal to 2. Which is the case we actually care about. So in that case, there are lots of ordinary p-adic modular forms which are not classical, and you should think about this in terms of the Galois representation. The Galois story is that, so what does the Galois representation of a weight k overconvergent modular form look like? Well, on inertia, it's ordinary, and there are some powers of the cyclotomic character, and they're these powers. Sorry. And so basically, when k is bigger than or equal to 3, the powers are strictly decreasing, and so this representation is automatically de Rham. But when k is equal to 2, well, the Galois representation on inertia, it now looks like sort of cyclo, 1, 1. And so such a representation is not necessarily even Hodge-Tate, let alone de Rham, but it's de Rham if and only if the sort of 2x2 block is Hodge-Tate. Okay? And so going back into the world of p-adic modular forms, I mean, there's some idea that the 4 Hodge-Tate periods of this Galois representation live on these 4 components of the ordinary locus. I'm not going to really try to make that very precise. And so what you feel is that the main difficulty in proving the classicality of this weight 2 form is sort of extending it over to here, and then it should be easy to extend it over to here. And so in fact, that's exactly what happens. So if I introduce an extra region in this space, there are the kind of partially classical modular forms that we considered in our previous work. And those are the things which live on this region, this whole region, which I'm going to call xm star. So the locus where h1 is multiplicative, but you put no condition on h2 mod h1, it could reduce to sort of alpha p, and the a could not be ordinary. So what is true and rather easy to show is that there's a sort of 4-term exact sequence, and I'll tell you how you should think about it. So we have some kind of space of partially classical modular forms, and I'm just going to write the kind of support conditions as a subscript now. Where the 2 cohomologies on the outside are sort of the cohomology of maybe the dagger neighborhood of this region. This is sort of overconvergent modular forms as it was before. I've just changed the notation. And so you sort of know what has to be the sort of complementary thing. It's some kind of cohomology of this region, but with support in the complement of the thing we were taking the cohomology of before. And this is this kind of, well, all of these spaces, we call them sort of some kind of higher p-adic modular form. And so now there's an easy classicality theorem, which we are also essentially using. And this is the one which just uses the ordinarity, and it says that these guys are classical. So this sort of R gamma M star So in other words, all you have to do to prove a form is classical is show that it's in the kernel of this map, which means that it comes from here and thus is actually classical. And so we call this map the Cuson map. And so if you believe the story that I'm telling you, you should believe, maybe, or well, this would have been a fantasy like 4 years ago, that this Cuson map, it should really be detecting something about this Gala representation being de Rham, and thus really something about the Hodge, this 2x2 representation being Hodge-Tate, and thus something about the Sen operator on this 2x2 thing. So you might fantasize that this Cuson map has something to do with the Sen operator on the cohomology of the Siegel threefold. And this is exactly the kind of thing that Louis proved. And I'm not really going to be able to, yeah, sorry, I didn't time this very well. I'm basically out of time. So I've essentially explained nothing and all the work is yet to be done, but that's life. So now use very fun point of view on periodic Eichler Shimura plus its generalization in the work of Juan Esteban Rodriguez Camargo. To relate Cuson to the Sen operator on the Tate module of the surface we're trying to prove is modular. Okay? And yeah, I was hoping to at least explain the precise relation, but I'm out of time, so that's it.
So is there any question? Is it possible to state in simple terms what the relation is between this map and the Sen operator?
Yeah, so yeah, I mean, I can maybe explain it in like 1.5 minutes. Is that okay?
Great.
Since you asked the question. But it really is exactly what Louis proved in the modular curve. And the remarkable thing is that this sort of situation looks exactly like the case of the modular curve, this sort of 2x2 block in just before. Okay, so what we prove is something like there's some kind of periodic Eichler Shimura. So maybe I won't define this, but I think you know what it is. So let H hat 3 lambda 2 be weight, maybe ord, weight 2 ordinary completed cohomology. Then, so there's sort of two statements. So first of all, there's a sort of Eichler Shimura decomposition in the sense of Louis pun, which is that there exists GQP and hecastable filtration on ordinary completed cohomology where the GERs are exactly the spaces of ordinary p-adic modular forms. So the GER I for I equals 0, 1, 2, and 3 is the sort of H0 MM omega squared ord H1 M et omega squared, and then H2 at N and so on. It doesn't really matter because we're not going to use the rest of them, still with words. And the Sen operator, so this has a Gala action, and the Sen operator, by what you'd sort of expect, the Hodge-Tate rates. Well, it depends on your convention for Hodge-Tate rates, but this is going to be 0. This might be 1 or -1. And okay, so
That's integral or?
No. Yeah, and I'll make a comment about that. No, sorry. Everything is. Yeah, I tensored with QCP, didn't I? So yeah, nothing is integral. And so the point, and this was sort of Louis-Pon's idea, is that okay, so you have two steps in this filtration where the sen operator is literally acting by zero, but then there's an extension where the sen operator is certainly not literally acting by zero. And so the sen operator defines a map which goes from this graded to this graded. And the way it's defined is, okay, this is the quotient. You lift to the sort of extension of these two guys. You apply sen, that now maps to zero here, and so you get something here. So it's just a snake map, exactly as in Louis' paper. And this has the same kernel and co-kernel as this map Poisson, which went between the same two. And so what I should say is that, of course, I mean, this version of p-adic Eichler-Schmor is actually kind of crappy compared to like other people's versions of p-adic Eichler-Schmor. In particular, there's an integral version, which is some work in progress of Juan, Esteban Rodriguez Camargo, James Newton, and Anna Cariani. Sorry, that wasn't in alphabetical order, which is kind of completely integral and also varying over weight space. But the nice thing about Louis-Pon's technique is that it also tells you a lot about completed cohomology without taking the finite slope part or the ordinary part or finite slope part at all, which of course we're not really exploiting here because we are taking the ordinary part. But yeah, it's completely amazing. Sorry, that was more than 2 minutes.
Perhaps to not be too late, if you have other questions, you can ask the speaker afterward, and we thank George again.